Welcome. I have a couple of announcements before I introduce our speaker. Hopefully you saw on Canvas that we are not going to have class on April 8th because class will be at the same time as the eclipse. So no class on April 8th, but there's a summary from the week before, 2 weeks before, that will still be due. You're encouraged to do it before spring break, but the last day that you can turn it in is still April 8th. You're welcome to do it before spring break though. Okay, so now I'd like to introduce Daniele Visioni. He is an assistant professor in the Department of Earth and Atmospheric Sciences, where I am. He did his PhD at the University of L'Aquila in Italy in 2018, specializing in atmospheric chemistry and physics. And then he came here as a postdoc, and then a research scientist, and then last year became an assistant professor. So thanks.
Thank you. Does it work? Okay. Thank you, Andy. Okay, so yeah, this is the title of my talk. And as somebody already pointed out, I'm actually going to start from the last of the questions and sort of then move back up. And the reason why I'm going to start from the last one is that, and this is connected to the eclipse, it's okay if the moon is the thing blocking the sun. It's maybe not as okay if we do it. So we'll try to work towards sort of what are the ethical implications of the idea and concept itself of climate intervention. And to me, in a way, the most important part is why, right? So I'm actually gonna spend what I feel like is quite some time setting the context, both in terms of future climate change scenarios and CDR, carbon dioxide removal. I'm sure you've heard a lot more about that by now. And why analyzing these two things together sort of bring us towards the idea that maybe we do need to study climate intervention. I'm going to try to define better what it is, because we might actually need it. And then finally, I'm going to talk about, well, how do we study it? What are the issues we face, and sort of the research that we do here at Cornell. Okay, so the first one, right? So maybe some of you are familiar already with this figure. This is from the IPCC report, actually from Working Group 1, the physical basis. These are what are called burning ember diagrams. Essentially, they are ways in which the IPCC has found a way to sort of communicate the risks connected to climate change. I really like this figure for one main reason, which is it does indicate how nuanced risks also are when it comes to climate change. This figure indicates that it's not true that there's no magical thresholds above which risks appear, and there are no risks before. Risks is a nuanced concept that has to do with more than just the physical impacts, but also that not all risks increase linearly, and that some risks might appear earlier, some risks might be actually much direr before, and some might not, right? So you can see here how, well, with two sort of different definitions of what the global mean temperature is, there is, sort of a low risk where we are now for maybe a lot of things. There is some risk to unique and threatened system. Also, this says how many different kind of risks there can be, right? Risk associated with extreme weather events, distribution of impacts, where are all the impacts happening, global impacts. And this is saying, where we are now is a place where we can already start perceiving some of the impacts of climate change. But for most things, we might agree that risks are moderately low, even though we start to perceive them. But then as we move forward and as warming continues, it might very well be that a lot of these risks could go up. And for some of these things, actually a lot more risk than now. So the additional level of risk due to climate change might appear pretty soon. And this is sort of one of the reasons behind agreements like the Paris Agreement, right? It says we should try really hard to limit warming below 1.5, at least 2 degrees. Some of them might actually not appear as fast, but they're still there. So there are many reasons why the fact that we might not be able to stay just below 1.5 doesn't mean that we need to give up. Where does this, right, and this is sort of a summary figure. One of the things that is sort of impossible to communicate in a figure like this also is the uncertainty that we have for a lot of these projected impacts. But nonetheless, a really good figure. How is this built? Normally, the way in which this figure is built is, of course, they say, well, first of all, to study these hypothetical future scenarios, this hypothetical future, we need scenarios that we can analyze with climate models. And this is essentially what the IPCC, what the Climate Model Intercomparison Project does, right? They say, okay, we're here. We know how much CO2 emissions there are now, but then it's pretty hard to figure out how much emissions we're going to have in the future. This is going to depend not just on physical constraints. It's not going to just depend on, for instance, the global carbon cycle. It's also going to depend on policy, on changes in policies, on human behavior. It's going to depend on a lot of things. So we cannot talk about future risk if we just focus on one possible future scenario, because we don't know how probable that scenario is going to be. So the IPCC takes this approach of being sort of agnostic about the probability of future climate scenarios and say, okay, let's explore multiple scenarios. Let's explore some in which CO2 emissions continue growing, some in which we do enough work, but probably not enough. Emissions peak eventually, maybe in the 2040s, and then they start going down. And let's also explore scenarios where we actually manage to go to zero emission and maybe even net negative emissions already by 2060. And then let's see what happens to global mean temperature first, and then to all the different risks. Right? So this is sort of an approach that says we cannot predict the future, but we can be prepared for multiple futures and understand which one of these futures are negative and which one are more positive. And none of these sort of has any implication of endorsement. We're not saying we're simulating a world where warming could be 5 degrees because we might like it, but just because we also need to know things that are maybe even extremely uncertain, but it doesn't matter because there might be things we don't know or things we cannot predict. So this is sort of the philosophy of behind a lot of these. The main point is also, though, that between this figure here and this figure here you only see global mean temperature. Here you also see global mean temperature. Well, if we only wanted to know what the global mean temperature increase is to a different level of CO2 emissions, we wouldn't even need the kind of incredibly complicated global climate models that we do. Predicting global mean temperature, projecting global mean temperature given a certain amount of CO2 concentration is really just a physics problem and not even a hard one. The sample that I always make also in class is that Arrhenius, already 200 years ago, actually did a pretty good job predicting what global mean temperatures would be if they kept burning coal. So this is actually one of the very first scientific papers that discussed this issue and actually tried to quantify. He did a good job. He did a pretty good job for the time. He said a simple global calculation so that the temperature in the Arctic would rise about 8 to 9 degrees if the carbonic acid increased to 2.5 to 3 times as now. That's not bad for the time, even though he missed some parts of physics. But so if we just wanted to know global mean temperature, we could do a lot of the things that we do just with small energy balance models. But of course, risk, it might be tied to global mean temperature, but it's not the only thing driving it, right? And so the reason why the IPCC spends so much time and we do so much work in climate models is because the things we care about are not necessarily the actual physical global mean temperature, but all the impacts that might be connected to that. So for instance, the last IPCC reports that figure like these that tried better to explain to the global public and to policymakers what are the actual impacts that might come out of increasing global mean temperature. This is just one example of many, and probably sort of the easiest one, because how hot temperature extremes over land would change. Precipitation would be much more complicated. But nonetheless, it is interesting to note, how would the frequency of events change, right? We know that even now, extreme heat events are more likely to occur than in the past. They might also get hotter. So intensity and frequency might also be things that maybe change differently, or maybe one changes in one sign or more on the other. But this is a very useful figure to say, okay, if we manage to keep temperatures at most 1.5, like the Paris Agreement asked us to do, maybe we can prevent future global hot extreme events from becoming more than 4.1 times, of course, with some uncertainty, more likely compared to the past. Same for hotness. But this also says, that the more we go, the further we go in time and in warming, things might become really bad. And we use climate models generally to try to figure out how a lot of these change, not just because we're curious and not just because we want to warn people, but also because, if we're building a new building and we need to know how much money to spend into isolating it and into making it more resilient to warming, how much AC we're going to need in the future, we need to know also information like this. I come from Italy. I go back sometimes in the summer, and honestly, like, my parents are amazed at the fact that up to 10 years ago, nobody would have even thought about having AC in their house. But now it's starting to become almost impossible to live in the summer. Even I come from a place that's pretty high up in the Apennines. Nonetheless, for someone, especially that gets into their 60s, it's pretty dangerous to stay in a house with no air conditioning at all, right? And maybe the grid is not particularly prepared. So these kind of analyses are not just for warning, they're also just for preparation. The last thing is, of course, not all the ways in which we might use the scenarios are for things that might matter in the short term, or even for this kind of short-term planning. Some things might be for even longer-term planning, right? A figure like this actually indicates that unless we're really wrong and about what high sheet instabilities look like, it looks like all the way to 2100, global mean sea level rise would not be that much different between scenarios. Even in 2060, they all sort of look the same. But then maybe there are things for which we might want to look much further and say, look, even if right now we settle on a scenario that actually doesn't have that many more CO2 emissions in the future, these might still lead to very high sea level rise 300 years in the future. And these are all things that we need to know, especially for much, much longer preparation or just to know them. So all this to say, well, this is how we treat scenarios. And so in all of these scenarios, it makes sense to ask, OK, at this point, knowing this and knowing maybe also this, we might ask the question, OK, what would it take for if we really wanted to stay below 1.5, right? And this is sort of where the exploration of scenario goes just beyond the simple physics, but just ask, like, how would we need to change our emission scenarios? What kind of strategy, the mitigation strategies we would need? And a figure like this is from a National Academy of Science report on negative emission technologies, or carbon dioxide removal, as now it's called. And it's sort of making the case of the fact that, well, you cannot carbon dioxide removal your way out of the problem of too many CO2 emissions. We know that for many reasons. The first one of them is because we actually emit a lot of stuff. So if we continued with business as usual, there is no, considering that most CDR technologies, first of all, we don't know if they can be scaled up, but they're really energy intensive. If we can assume that we get all the way to 70 gigatons of CO2 per year, and we can just remove all of that somehow magically, that's never going to work. The point that the National Academy of Science made in that report, and that the IPCC also often makes, is that, well, we can do a lot. We should definitely, and we can do a lot of effort into mitigating our emissions. That's the first and the main thing that we can do against future climate change. But it's also unlikely that for many reasons that this is going to be enough, especially in the short term, to make sure that we stay below Paris Agreement thresholds. There are sectors that are hard to abate. There are policy reasons. There are many, many reasons why this might be possible, and it will certainly be possible in the long term. But there's a big question mark about how much can you mitigate, especially in the short term. So at this point, we might say, OK, we're going to try our best and then come up with these technologies that allow us to both reduce the amount of emissions that come out of a lot of our system. So sort of things like carbon CCS, for instance, but also that then eventually we might need carbon removal technologies, technologies that actually physically remove CO2 from the air. Well, this figure, there are many ways that one can look at this figure, but one point that one can make is that these kind of figures that make projections about potential future scenarios, by 2100, this is one that is considered sort of moderately conservative when it comes to CDR. It still indicates that by 2100, to stay below 2 degrees, so not even the most ambitious of all the pathways, it would take 20 gigatons of CO2 per year, negative. So it means that we would need to remove from the air anywhere between sort of a bit less than half of what we're actually putting out. So the point beyond this figure can also be that, well, this means that right now, in 70 years, we need to develop a global infrastructure that would allow us to capture that CO2 and then so prevent some of the effects of climate change that is comparable in scale to the current infrastructure, societal infrastructure that we have now. Maybe we can convert some things, maybe we cannot, but the point is this is going to take a lot of effort, and this is not even for the most ambitious scenario. There are many, many different examples of carbon dioxide removal methods. The point to make now is that of all of them, all of those that are in the figure, this figure and the next, none of them have really been proved to be able to work at scale. This assumes that a lot of them can, okay? Like none of these methods alone would do 20 gigatons of CO2. Maybe 5 or 6 of these methods together, scalable at the largest scale they can, maybe they could. But for now, none of them have been proved. Nonetheless, based on this figure, based on the figure before, and on the risks that we know that might come out of not doing this, it does make sense to study a lot of these and say maybe we can increase coastal blue carbon or do accelerated chemical weathering of rocks. This means actually really like spreading rocks that are pretty good at absorbing CO2 like olivines. We can try direct air capture, especially if we have energy sources that are very cheap. Right, so for instance, Iceland might afford to do direct air capture because they have more geothermal energy that they can use. We can try afforestation, reforestation, BECCS. There are plenty of things that one could do over land. There are also plenty of things that one could do over the ocean. The ocean covers most of the world, and so people are asking, well, are there things that we can do over the oceans to make sure that they capture even more carbon than they are right now? While some of these over land have now been studied for a while, when it comes to studying carbon capture method, carbon dioxide removal methods over the ocean, there are so many more unknowns even. First of all, first point is being that the ocean is so big, and so they are so vast, and they're so deep that we barely know what happens to circulation, to general circulation over the ocean, let alone understanding how the carbon fluxes work, especially across different layers. But anyway, this doesn't stop people from proposing very different things, maybe artificial upwelling, direct CO2, hiding CO2 under the oceans, nutrient fertilization, that was pretty big in the 80s, now it's coming back, like a lot of things. Seaweed cultivation, lots of things, right? The point behind all of them, though, is that really at this point in time, we have questions over whether many of these even work at all. And for the ones that work, like we know that, for instance, chemical weathering works. But the question is just, do we even have enough olivine in the world, or how much would it cost to extract all of the olivine that we would need to reduce a substantial amount of CO2? So a figure like this does hinges on the fact that by the end of the century, we were able to do all of this amount of carbon dioxide removal. And this is without even considering the fact that a lot of times, right, governments have really caught up to this narrative of net zero, of the fact that we don't need to sort of assume that we need to cut all of emissions and bring our emissions to zero, that there's always going to be a part that we can actually remove through CDR. And so many, many governments have a lot of policies that are sort of 1.5 related, Paris Agreement related, and that have a lot of hope into future CDR, right? And the climate action tracker actually has a lot of these figures like this. I'm not even sure this is the most updated, that actually talk a lot about these. Most governments have absolutely no clue what they're talking about when it comes to their targets, especially 2030. 2030 is 6 years from now is probably 5 years and a half from now. And none of these CDR methods have been proved to work at scale. We know that by 2030, almost none of them will. Nonetheless, countries really strongly pledge things in their 2030 plans that don't exist, not to mention about what's in their most optimistic scenarios. So here, that's, for instance, when we go back and now start to thinking about, well, what of these scenarios is more probable in terms of future climate change, we must also remember that a lot of the future scenarios of governments, whether it's the US, European Union, China, every government, claiming that something is going to happen to their emission by 2050, there's a lot of gaps. There's a gap between the optimistic scenario and what countries pledge. There's a gap between what countries pledge in the long term or what countries pledge in the short term. And finally, there's a gap between what countries pledge even in the short term and what countries are actually doing towards those pledges, so the policies. So, you can sort of do with it what you will, but definitely there's an increasing sense of a gap between what countries are assuming can happen, our knowledge of how much risk there is out of future climate change, and even climate change right now, and where things stand. So it does make sense to look at a lot of these carbon dioxide removal methods, but none of them actually are completely free of different kind of risks. And there are a lot of things that could go wrong with these. So just as a few examples, right? A lot of the methods that I sort of skim through when it comes to carbon dioxide removal, not all of them are risk-free, in the sense that there might always be risk attached to them, especially with ocean carbon dioxide removal. We know that there might be risk, and so we need to be able to evaluate those risks and wonder whether it makes sense to even start large-scale deployments of some of those CDR techniques. If there might be risks, we don't know. It may distract us, talking too much about CDR may distract us from reducing emission. That's an argument that people have made for 40 years. Whether we haven't reduced emission because of that or just because of many, many other reasons, that remains to be seen. But it's definitely one of the other things. There are other questions as well, though. These are all interesting questions of research that people that do carbon dioxide removal sort of face every day, right? Who would be in charge? How do we decide how much CDR do we need? How do we decide how to regulate it? How do we make sure that local communities are also benefit, right? If this is about a direct air capture plant, those are noisy, for instance. How do you compensate a local population? How do you make sure that those kind of direct air capture plants that would actually suck the air out of the atmosphere, remove the CO2, how do you make sure that these don't end up being in poor communities that don't have the means to fight back, right? There are also more sort of scientific questions, like how do we measure progress? How do we measure CO2 fluxes? Anyone that has ever worked on ocean carbon fluxes know how hard it is to measure carbon fluxes at the surface of the ocean. So how do we know that we're doing something? And maybe locally we measure that it's reducing CO2 concentration, or maybe 100 kilometers from where we're measuring, CO2 fluxes are increasing upward. So there are a lot of questions with all of these, right? Some of them have to do with climate justice. Some of them have to do with actual environmental risks. Some of them have to do with the economy of scale, many of them. So just to summarize, right, for this first part of the talk, here we are. We are here where I put this star. We are starting to perceive an increase in many climate impacts. Again, the IPCC reports and many national reports are starting to highlight all the risks that we can see and we can already attribute to climate change that has already happened. And we know that if we keep whatever we mean for business as usual, whatever we mean for in terms of if we keep emitting as we're doing now, these climate impacts would increase. We know that. There's really no escape. Like physics is really hard on this. There's no escape from this. So the first thing that we should really do is cut emissions as aggressively as we can. We should prevent emissions from increasing, and that is already proving to be incredibly hard. In this sense, we could say that there's a lot of uncertainty. Of course, we can acknowledge that there's uncertainty, and in this case, the uncertainty is mostly on the political and economical side. We don't know how well we're going to be able to cut emissions. It depends on all of us. It depends on governments. But honestly, if we're trying to sort of predict something for the future, it's really hard to do that. And the main point being, even if we were super aggressive about cutting emissions, what the most that we can do here in just this framework is make sure that climate impacts don't get too worse, right? So what you see here, and as long as you're talking about a scale that is in this century, none of what we do with emission reduction is going to reduce climate impacts. Maybe we can reduce risks by increasing adaptation, for sure. But this means that if there's something looming in our climate future, some of what we call tipping points, if there are some destabilizing points of the system that are pretty close, just cutting emissions probably will not do it. And this is sort of where the narrative around carbon dioxide removal comes in. Eventually, we can cut emissions, prevent impacts from getting worse, but eventually we are gonna need to restore our environment to one with lower CO2 concentrations. We just know that's gonna have to be, unless we want a massive change in the way in which we perceive and live in this world, okay? And when it comes to CDR, as I said, there are many, many, many uncertainties over how much we can do, how much is feasible, or how much is just to do. There are incredible questions over all of these. So, and at this point, we say, OK, so what do we do? And here is sort of where we're starting to see very different narratives. There are people saying, well, we should just adapt, right? There's nothing else. We should just adapt. Countries like Taiwan or like other small island countries are starting to think, how much would it cost for us to prevent sea level rise? For instance, and Taiwan maybe can afford it, but other small island nations in other oceans maybe can't. But Taiwan is making already like huge efforts to build sea level walls against sea level rise that are going to prevent that from happening, right? So many people are going to say that. Some people are starting to give up and say, well, there's just nothing to do. We should just prepare for the worst. And that's just, if we just look at this picture and this green, we just prepare for the worst. In general, I could make a lot of points here, right? I'm just going to make one. If there's one thing that we know is that here, where we are now, is also not safe, right? We're seeing it. Here I have two figures, sort of from the purely physical perspective. One of them is what we can measure from satellites and saying, where we are here is not a place that is safe already. We're already at a point where we're absorbing a lot of incoming solar radiation, much more than we were in the past. And of course, the physics of the greenhouse effect is meaning that the planet needs to sort of heat up to increase its long wave emission and sort of get rid of all of the energy, but that is not going to happen fast. So our planet is currently gaining heat, is accumulating heat year after year. And none of these things that we're proposing here are going to make that become any better. There's just no doubt about that. And this is particularly relevant, and this is a thing that we thought about a lot, right? There's now a lot of talk about a human right to a stable climate. There's also a group of young people, I think in Minnesota, pursuing the Biden administration and the US government because they claim that in the Constitution there's a right to a stable climate. So these kind of discussions are blowing up, and they're going to continue a lot in the future. Do we have a right to a stable climate? Well, if we do, we're already not in one. And reducing emission is not going to help at all. I mean, it's going to help from making it worse, for sure. And so we should absolutely prioritize that. But it's also not going to make it any safer at all. So even if we start talking about these, right, and I actually feel like if you read, for instance, this litigation and how it's proceeding, the Department of Justice does make some good points about the fact that we don't even have a definition for what a stable climate is. And so defining that as a constitutional right would open up the door to a lot of different things. But in general, if that's something we are concerned with, and we think it's right, and we should discuss about how do we prevent things from getting worse right now, how do we give, in a way, hope, but also how do we buy ourselves some time to develop all of those technologies, it might start making sense to think, well, what can we do now? And maybe, based on this figure here, we can say, well, maybe one of the things we can do is prevent more solar radiation from getting into the planet. And so we can start discussing about what normally we call solar radiation modification, solar geoengineering in general. Can we reduce some of these impacts by artificially reflecting part of the incoming sunlight to prevent more warming from entering the system and buying us all the time that we need to do all of the other stuff that we need to do? The National Academy of Science had a report about these. The National Academy of Science they really love having reports all the time. But actually, this was a really good one. This was about saying, hey, we know what SRM is. Now we just need to really get serious and do research into it a lot. Nobody really heard them, but nonetheless, there was actually a pretty interesting report. Essentially, in this report, first of all, definition, right? The definition of SRM, or climate intervention, as now people are preferring to call it, is defined as the deliberate modification of Earth's climate. So this is important. The deliberate modification of Earth's climate. We're deciding, it's not just a byproduct like CO2 or like cirrus clouds out of planes or whatever. This is actually, we're deciding to do something to modify the Earth's climate through the reflection of a portion of incoming solar radiation with the specific intent to reduce some of the risk produced by global warming. And the National Academy of Science defines mostly three methods. There are other things going around, but these are sort of the ones that scientifically make the most sense. And say one of them is the one that I'm going to talk about, the injection of sulfate aerosols in the stratosphere. We know that it would work because it would mimic the effect of explosive volcanic eruptions. But they say, there are others. Maybe we can try to reduce high clouds with cirrus clouds that trap outgoing long-wave radiation in order to reduce their concentration. Except that, honestly, almost nobody has any clue whether this would work because cirrus clouds are complicated and we barely know them. But nonetheless, it's one of the proposed methods in the study. And the third one would be, well, we know that ship tracks leave persistent brighter clouds over the ocean. So can we actually increase the reflectivity of low marine clouds to make sure that even a bit more solar radiation is reflected? These are the three main methods. And now I'm going to give you some example. Here, the work that I've done starting from my PhD has been all around what we call SAI, stratospheric aerosol injection. So asking whether it would make sense to reduce risks from climate change by reflecting solar radiation before it even reaches the troposphere where we live, but just reflecting a part of that in the stratosphere. The first question, it would even work, which actually surprised, of the three methods, this is the one for which we actually have much more even understanding and proof of the fact that it would work. And the main reason we do is because we have had volcanic eruptions in the past. And when a volcanic eruption is very big, it's in the tropics, it's very explosive, and it throws a lot of sulfate in the stratosphere, we can see in the temperature record how there's always a drop after a big volcanic eruption. The last one being Pinatubo in 1991, that is probably the best studied, that cooled the planet in a year by 0.2, 0.3 degrees, so a third of all the global warming at the time. So we know it would work. We honestly, we understand the physics well enough to be quite sure that globally, at the global level, it would work. Up to the point that, this has been proposed already a lot in the past. This article is from Paul Crutzen. He was a Nobel Prize in chemistry. He was the guy that saved us all, together with another couple of people, from the ozone hole, because he was one of the first people to propose the mechanisms behind ozone destruction. And in 2005, it was considered a large environmental error. And in 2005, he had this paper where he said, look, we can see that cutting emission reduction is not going that well. And so if temperature keep rising this rapidly, then climate engineering, climate intervention in the form of adding sulfate to the stratosphere might really be the only short-term solution to the policy dilemma, which is we see temperatures are rising and we're not doing as much as we could about that. He says a lot of caveats in this paper, and it was not well received at the time. He only managed to sneak it through because it was that important at the time. But honestly, he was the first person to sort of say, hey, this just makes sense, okay? Stop wasting time and let's study this, because it might actually be the only solution to the policy dilemma of emissions and risks. So just a little bit of chemistry, right? So we know it would work. We've seen volcanoes throw large amounts of SO2. They do that just because that's what's behind under the ground. Once they get to the stratosphere, we put sulfate in the troposphere all the time through other means, through industries, to burning coal. Dimethyl sulfide does it from the ocean. There's a lot of ways with natural systems that throw a lot of sulfate here in the troposphere. Well, there's a pointer, but here in the troposphere. But in the troposphere, there are clouds. They rain out, and so that sulfate doesn't stay too long. In the stratosphere, above these gray lines, the sulfate doesn't have that many ways to go, except large-scale stratospheric circulation and gravity, and so it can stay a lot longer. So there's enough time for the SO2 to oxidize with OH, and to form these tiny aerosols, these tiny liquid, supercooled liquid suspended particles that can stay up to a year in the stratosphere. And they are exactly of the same size. You might recognize these as sort of the same size as the wavelengths of visible light, which make these quite perfect in terms of optical window for reflecting sunlight. So we just know that these particles would reflect sunlight. Something like Pinatubo probably reflected 1 or 2% of incoming sunlight, so it's not enough, for instance, to limit photosynthesis, because plants are not that limited by direct sunlight, but enough to affect the energy balance. That's not all they do, though. One of the main examples is the fact that, well, things that reflect normally tend to also absorb. When we have energy not all the wavelengths are the same. And so particles in the stratosphere also tend to absorb some part of the incoming spectrum, some part of the outgoing planetary radiation, and locally heat up the stratosphere. This is one of the things we know. We've observed at Pinatubo, and that is one of the things that also means that this is not just a perfect solution, because it does affect and perturb the climate in other ways. There are many questions that we can ask when it comes to SAI. Right? The first one that people always ask me, up to the point that I wrote a paper actually with Christy as well here, but also that I ended up putting these slides all the time, which is what happens to the sulfate in the stratosphere. It is undoubtedly that sulfate has a lot of negative effects. It is also undoubtedly that we actually put a lot of sulfate all the time, and that actually what makes SAI so, in a way, I wouldn't say good, but definitely interesting to think about and study, is the fact that we would need only a tiny fraction, even if we wanted to offset all of global warming, right? So in this figure up here, you can see the cumulative amount of sulfate deposition that has happened since the beginning of the Industrial Revolution. It's a huge amount. And the red line is the projection for the future. And the blue line is how much more there would be if we were trying to offset really all of climate change with something like stratospheric aerosol injections. It's a non-zero amount, but it's also small if we compare it to the amount that would happen just for the other things that we do. This is just the same thing, right? Right now, we're through anthropogenic emissions, we're emitting over 40 teragrams of sulfate in form of S. So if it's SO2, it's 80 teragrams. And maybe this is going to go down because of Clean Air Acts all over the world. But in general, if we really wanted to, we could probably take a small part of that and just bring it upward and try to reflect some solar radiation. This doesn't mean that this is not something we should be concerned about, but sulfate is something that we're familiar enough with to not be one of our main concerns. But there are others, right? And the main one is that, again, once we're trying to understand the surface impacts, we need to ask, well, what are we comparing against and how do we define risks, right? Nobody lives in the global mean. I could show you a figure that says, look, with SAI, we can cool however much you want, but that is unfair because, again, nobody lives in the global mean. However, we can start asking, what are we looking at in the future and how would impacts look like? So as an example here, we said, okay, let's imagine how different levels of warming impact the climate differently, right? And since we only had one sort of future pathway, we said, okay, let's look at this future pathway compared to different historical periods in the past. So you can see here how much the planet is warming compared to previous periods that had lower global mean temperatures. And then we said, okay, let's try to simulate different amounts of SAI to cool the planet back to those different periods. And then we said, okay, and then let's extend this comparison and say, how would a climate cooled by SAI look like compared to a climate that had the same global mean temperature but with less CO2? And this is just one of the points to make is say, well, if you just try to cool by a little bit, if you just try to prevent warming from getting worse, actually, the dark shaded lines are essentially places which is impossible to tell whether this is a climate that was cooler because of less CO2 or that is cooler because of SAI. And most of the planet doesn't look that different, honestly, in our simulations with the climate model and so on, but that's honestly what we find. But then what we find is that the more warming you try to offset, the more warming you try to hide, whether you think this is because of a different period or because it's more warming or whatever choice you make, well, the more these differences become evident. This is sort of one key message of saying SAI should never, ever be sold as something that can in itself solve climate change, because we know that the more we try to cool, the more all of these side impacts that we see would impact the climate, would result in a different climate. And what we want to try is to avoid having a different climate. There are other worries as well here, okay? The main one being, and this is a paper that we wrote with actually a group of ecologists that got interested in this field that said, okay, let's get all together and let's try to think too about what actually these would all do to ecosystems, right? Ecologists are incredibly worried about what climate change alone is doing to a lot of different ecosystems. But one of the things we pointed out is that, of course, the main risk, if we really try to offset all of the warming from CO2 with something like climate intervention, we would end up in a case where we're hiding such a massive amount of warming that if we ever suddenly stopped, we would end up in what we call the termination risk. So we would end up with a climate that suddenly, in a matter of 5 or 10 years, goes back to all the warming that we tried to hide. And this is the part that is the worst for ecosystems, right? Ecosystems have a hard time, like humans can move and migrate, and even there are challenges with borders and all of that. But on the other hand, trees can't move that fast. Most species cannot move that fast. So if we end up in a place where we change the climate this fast, this could be a huge risk for ecosystems. On the other hand, the ecologists agreed with us, right? We had like that indeed. If we try to keep temperatures constant, we might try to prevent a lot of the impacts that we care about when it comes to ecosystems as well. So does this mean that we have now a global thermostat to control? Of course, with CO2, CO2 is our main global thermostat, right? Depending on how much more we put, we know how much we're going to increase global mean temperature. The less we put, or the more we try to remove, the more we can sort of reduce global mean temperature. Is geoengineering, climate intervention, another one of the things that can help us sort of tune this thermostat one way or another? Well, again, first of all, it is clear that compared to CO2, where we put these aerosols matter. There are many things you can do with them. So maybe one could say, well, it's actually more correct to say that it's not a thermostat. Maybe it's a control panel. How much control can we get in over our climate if we're able to sort of decide how much cooling or warming we could get based on adding aerosols to the stratosphere? So again, maybe we could imagine a control panel like this and say, can we tweak all of these things to get exactly the climate we want? Again, if there's one thing that we found with our research is that it is absolutely, we do not have such a great knowledge, such a perfect knowledge of our climate that allow us to have a control panel like this that we can perfectly tweak. There are teleconnections, there are things that are connected one to another, and there are fundamental constraints. So thinking about climate as a thermostat is wrong because we know it's not just about global mean temperature. But on the other hand, we would be completely blind if we tried to imagine this as a control panel. We are not claiming, nobody's claiming, and the research clearly points to the fact that SAI is also not a magic solution that can help us save the world perfectly. However, I have to say that here we've done a lot of work in the last 3 or 4 years. Here's 2 of our grad students that recently, last year, graduated. One of them is in Hong Kong. The other one is at the National Center for Atmospheric Research in Boulder, continuing this research. We have managed to do a lot of work trying to map out better this space and to figure out really what are the fundamental limits to what we can do. We know that if we reduce temperatures, we also reduce precipitation, but that also depends on interhemispheric energetic fluxes. If you cool one hemisphere more than the other, you shift things like the intertropical convergence zone that affects precipitation. And so we've done a lot of work sort of mapping out this space and trying to understand what are the fundamental limits and trade-offs. And really, if there's one thing that we've learned is really that we understand things okay, but we don't understand things perfectly. And so again, it is dangerous to claim that we have that something like SAI would give us perfect control over the climate. So now what is it that we're doing? Well, just like the first figure that I showed you where I had the different scenarios from the IPCC, we're trying to do the same thing and say, okay, let's try to sort of map out this entire space of ways in which it would be possible to do climate intervention and figure out what's the trade-off between them. So again, as the figure with the maps that I showed you, we could ask how much we can cool, right? We can put ourselves on one emission pathway and say, should we just cool at Paris Agreement level? Should we try to cool more? And then let's ask a question about how would we inject these aerosols in the stratosphere? When would we start? And what the differences would be? What happens if we terminate? What happens if there's a 2 years interruption because of an unprecedented event? What happens if we eventually want to start phasing it out for various reasons? And trying to understand better these trade-offs. The main one being, though, again, while true that this is not like a global thermostat, it is true that we need to start having the discussion about, well, what should this target even be, right? For some countries, it would be better to continue warming a little bit, maybe countries that are very high up, and so they actually could improve their agriculture. For some countries, the warming that exists right now is unacceptable because sea level rise is threatening them right now, or because heat waves are going beyond what's humanly feasible. So some countries might actually want to have more cooling. So actually understanding how much would we have to cool if we ever want to cool, it's a really important question. And so we're starting to study these trade-offs. This is just a sample of the scenarios that we run through our climate model to sort of say, hey, yeah, we knew this, right? We know that we can cool as much as we want with SAI and maybe keep temperatures at 1.5, that's green line. Maybe we can cool even more. But then say, look, these things are all going to have trade-offs. If we cool more, we're going to reduce global land, the hydrological cycle over land. We're also going to restore more sea ice, but we're also probably going to destroy more stratospheric ozone over the South Pole because of various chemical mechanisms. So we just need to be aware of all of these trade-offs and trying to figure out what do they mean, right? We're not, science itself does not give answer about what's good or what's bad, but just allows you to have sort of an informed decision and have a large amount of trade-offs upon which global population policymakers can decide. And there's a lot of the new work that we're doing right now. I just put out a few of the things that our group is doing. For instance, what happens if we start in 10 years from now SAI, or what happens if we delay these for 10 more years? What would it do to the heat content of the ocean? What would it do to ecosystems? But also, are there good reasons why we would want to delay? Or what happens, how can we understand all of the potential inconsistencies? So what happens if we stop for 1 year, 2 years, 3 years, after how many years of deployment? That's a lot of the work that Jared is in the audience is doing. Work trying to understand how would something like SAI reduce risk of Antarctic ice loss, right? And we found some really interesting results about how much where you're injecting the aerosols matter. We have Kian undergrad also here in the room that is doing a lot of interesting analysis, looking at the different ozone depleting cycles in the stratosphere, and try to understand how they would be impacted by different amounts. So there are just some examples, right? There's a group that I collaborate with at Rutgers University that does agricultural impacts that is, made some really interesting research, figuring out, trying to understand how different countries would have different optimal level of climate intervention that they would desire based on crop production. And this leads to question about, well, how eventually whose hand is going to be on the thermostat, right? Who's going to decide? Just as a parallel to CDR, I'm just going to say, well, when it comes to SRM, there are a lot of the same issues that exist for CDR, and in a way the same that exist for emission reduction. We know that SRM is not risk-free, right? We know that it's not a perfect magical eraser that is going to allow us to prevent as if climate change didn't happen. And it might be quite certain that it would affect the way in which we behave when it comes to reducing emissions, what's called moral hazard. Some people might say, this is spooky enough that if we tell people are going to actually want to reduce emission to avoid doing this. Some people might say, people are crazy. They're just going to say, oh, we don't care about climate change anymore. You can just solve this issue. There are going to be issues about who is in charge about this. Of course, large countries, powerful countries are going to have more leverage than small countries. How do we solve this? There are also issues that are very specific, for instance, to SRM, right? And the main one probably being, do we even have the right to do it? If we're already, as people usually say, well, we're already into a problem. Why are we trying to find a solution that is actually another problem on itself? Should we just try to sort of live within our means and not try to affect our relationship with nature even more? Again, if we assume that different countries might have different preferences, this is going to increase international conflict. And what if a country decides and just do it on their own? How would you stop a country like the US from doing it if they wanted to? They don't want to, but what if they wanted to? What if another country wanted to? What if it's a country that has a nuclear arsenal? It would interact again with issues like climate justice. And then there's a lot of, this is not to hide the fact that there's a lot of still interesting scientific questions that we need to solve. We haven't understood everything when it comes to things like stratospheric aerosols. I'm not going to claim these. So there's also a lot of science that we still need to be do. But personally, I see these issues as connected. So just to conclude, again, something like climate intervention, SRM, geoengineering is not a solution to climate change. It does not fix the underlying causes. That's no doubt. It does not fix all problems. However, we are at a point where, honestly, I have to say, I get asked all the time, and people are asking this question more and more. is doing this safer than not doing this? And it's going to be eventually, I feel like it's going to be hard to claim that we shouldn't do this because there are more risks in SRM than in not doing SRM. But the decision is not going to be up to me. It's not going to be up to singularly any of you in this room, probably, unless one of you becomes the leader of the free world or of the entire world. But people are going to start to ask that question. And we cannot just say, well, I don't know, but this is too dangerous to understand. We just haven't looked into it. This is already making its way into reports, IPCC, World Meteorological Organization, World Climate Research Program. It is already sort of being crystallized into climate policy. And so eventually we do need to give this answer, right? We need, and what all of my research into this field, what it has indicated is that these issues stops us from considering climate change as just a physical problem more than anything else, because there are so many issues when it comes to something like intervening directly in the climate that will absolutely ask for much, much more collaboration between climate scientists, social scientists, ecologists, a lot of different connections that maybe we didn't think we needed before. And eventually, the last point is that this also means that we're going to need new methods of understanding what it means to intervene in the climate and how to govern that, both in terms of the research, because research is not ethically neutral, never is, but in this case, more than anything else. But even on eventual deployment, this leads us to think, what international systems do we need in order to be able to govern this fairly? It's pretty obvious we can do something like SRM massively wrong and end up in an incredibly horrible place. But I do think, and I think that research does really show that it can also, there are pathways in which we could do this right and actually reduce suffering. And so this, to me, is the main reason why we need to study this issue. Thank you.
And then there. And then there. You go first.
Hello, first, thank you so much for your lecture. Also, I was just wondering, what type of effects does sulfur have when it hits, like, what type of ecological and environmental effects does the sulfur have once it returns to the troposphere?
Oh, you're here. Sorry, I couldn't see you. Right, so as I said, since there's so much sulfate, we actually do have a lot of understanding about what would happen once it comes down. It has a lot of, so first of all, especially when it comes from anthropogenic sources, so when it's being just recently emitted, it does end up being, ends up on our head and we breathe it in form of PM 2.5, PM 10. If it stays much longer in the atmosphere, it actually means that these particles would grow much larger than that, so that might not be that much of a health issue. But we know that PM 2.5 worsens when there are sulfate emissions. We know that ecosystems are affected by that. Soil acidification has been a huge deal for a long while, right? These mostly, and especially in the US and in Europe, where there was a lot of the Industrial Revolution, we know what that does to a lot of ecosystems. We know that this has brought some soils in a much more vulnerable place. So this is another one of the issues, right? And there are others that how would it affect hydrologically? It would affect how different components are metabolized by ecosystems. So we understand a lot of these things, right? Because for sulfate at least, we have a lot of the examples that come from studying it, how it has changed the system in the past.
Is working. Okay, yeah. So actually, my question was also on acid rain, since we do know that. I guess I'll just ask like this. Since we do know that's one of the effects, it can have devastating impacts on the unique forests of Washington State, Switzerland, and all of that. I was wondering if there's been any research done into alternative gases to use instead of sulfate.
Yes, there is. The main problem with that, yes, there is definitely other groups that have researched, you know, things that are not sulfate. You could think of calcite, because calcite is a basic, it's not an acid, so it's good. The main issue there, for me at least, is that sulfate is at least something that we have a good grasp on what it does. When it comes to any other components that we would try to put, their answer is that there's never been anything like that in the system before. So the unknown unknowns, the things we don't know, are much larger and would require a larger scale of testing. But this is not to do, I talk mostly about sulfate because that's what I study and that's because what volcanoes tell us. But this doesn't mean that it's going to happen through sulfate if it's going to happen at all, right? Just that for me is the perfect example of something we know well enough that we understand the impacts.
Thank you.
Oh, okay. So my question is, what is our next step after we get to 2030 with the Paris Agreement? Because I feel like the way that you were talking about it, it seemed like we're not going to get to that. Like, what do we do if we get to 2030 and we're just not there and not where we're supposed to be?
I think that's a wonderful question. Thank you. And it's a question that people are just asking. So first of all, we don't need to get all the way to 2030 to figure out. First, in the Paris Agreement, it doesn't say 2030 anywhere. But 2030 is sort of the threshold where we know where we're going to be above this 1.5 thing that the Paris Agreement have decided. And there's a lot of people that are starting to ask exactly your same question, right? What do we do? And in a way, once we'll be at the place where we know we've gone past 1.5, we're probably also going to be clear whether 2 degrees is something is going to be achievable or not, right? And so the question is exactly this, is how will societies, how will governments respond once this idea of the fact that we can stay below 1.5 is gone? And I see it in my personal experience, talking to governments, talking to policymakers, and talking sometimes to NGOs, even to groups like Extinction Rebellion, honestly, is that I see these going 2 ways. Either I completely give it like a complete sense of loss and giving up and say, okay, well, this means that this was all for nothing. Or a sense of like, well, then the apocalypse is coming. We should just, like, eventually a lot of that is giving up. And that can take the form of either, well, at this point, it doesn't make any more sense to be part of the civilized world, whatever it means, or just, oh, we give up and you continue doing what we're doing. And I think that the more that we talk about these issues, that people are going to also say, well, if the Paris Agreement has decided that it's so important to stay below 1.5, why don't we do this as well? And this is the question that I honestly, like, governments are already starting to wonder. And so I don't know what's going to happen in 2030, but I suspect that discussions over whether we should do this or not are going to really get into the mainstream 6 years from now. And we're going to have at least a scientific grounded understanding of things before we give an answer.
Oh, hi, Professor. So thank you so much for the lecture. You mentioned that you're from Italy, and you also mentioned that about air conditioning. So there's one industry that I found really interesting for me, which is the heat pump industry. Mm-hmm. So for heat pump, it is basically that can both heat and cool the room by transferring the thermal energy. And it has a lot of obvious advantages. For example, a completely electrified household by replacing the boilers powered by oil and natural gases. And second of all, Bloomberg says that it is the next $500 billion market since it can reduce the temperature. And last but not least, which I think the most important thing is, the government in Europe is actually having subsidies really high, that is up to, for example, 5,000 euros per installment in a household. However, the penetration rate for heat pump installation in Europe is less than 7%. So my first question is, why this is the case, given that heat pump has decisive factor than traditional heat pumps? Heaters. Like, for example, is it because of the supply? Is it because the price is so high for installation challenges? Or it is the problem for demand, where people don't know what heat pump is? And my second question is, if you can come out one strategy, what could that be in order to increase the implementation of heat pump?
Great, thank you. So yeah, actually, that's a very good point. And in a way, to me, it perfectly illustrates how there are things that would just make sense to do, and we're not doing them anyway, because is a complex concept, and also because people are resilient to change, and not in a good way, right? And so yes, this is exactly one of the examples. You mentioned one thing, which is, like the high subsidized, so like it's very heavily subsidized, and yet people are not doing that, because even if it's heavily subsidized, you still need some form of investment. And people are not that quick to make the connection between investments and things that would benefit them. And now, honestly, like the answer could be that one of the main ways to convince people to do it is because energy prices are becoming so high in Europe, especially compared to the US, that people are really starting to wonder, well, I would probably recoup the cost in 2 years. But this is an interesting point over the fact that people don't always respond to positive incentives as much as they respond to negative ones, and how much this is also something that be expanded for climate intervention. Are people not gonna discuss this in a serious way until something so catastrophic happens, and is at that point too late? And I think this is something that could apply as well, right, to heat pumps as well. You know, it would just make sense if we all did it, and yet people are not doing it because they have other priorities, because their preoccupation is to things that are much closer to them, so they're just not doing it. This is just how complicated the human mind is.
Yeah, thank you for a nice talk. And I think my question is related to the previous question as well. So there are like positive effect and the negative effect from the surface aerosol injection, or something like that. So does any previous study do like quantify the advantage and the disadvantage and like compare those and see whether it is good for like doing it or not? I mean,
Yes, and the answer, well, there's a easy answer and a complicated answer. The easy answer is that it is doable. Like there are economic models, there are these integrated assessment models that do exactly this, that quantify climate damage from an economic point of view. And so you can just plug in the same climate simulations that you do for climate change. You can do it for SRM. And what you find is that from a purely economical perspective, there is no reason not to do SRM, okay? And then if you do that, and then you say like, well, then why aren't we doing this, right? And then the question becomes, it's clear that humans respond to other incentives that are not economical. It is, from a purely physical perspective, if we were not social animals and if we did not live in a complex world, right now, there are probably 99% positive reasons why it would make sense to prevent the energy imbalance at the top of the atmosphere from getting worse by adding aerosols tomorrow, okay? But you would never see me arguing in favor of starting tomorrow, because there are so many things that have to do with things that are not the physical climate. And one of them, one of the things that I'm most interested about, honestly, is right now when we see an extreme event, it's already hard to tell whether, and it's even a weird question in itself to ask, has this event been caused by climate change? It has to do with a lot of things. You have to believe in the physics of the model and all of that. You have to understand how did you build your counterfactual. And then you have to talk about probabilities, right? This event has been made 20% more intense or 2.3 times a lot more likely. If you, on top of all of these, imagine what would happen to attribution science if we were doing something like SRM. Country A claims that the tornado that destroyed their crops has happened because of climate intervention. Country B that is doing climate intervention says, no, our models say that that's not the case. Who do you believe, right? So, and essentially this has to do with physical understanding and having a robust understanding of the system, but it has also a lot to do with trust, right? We've seen it for a lot of other examples like vaccination. Vaccines just make sense, and yet people really don't want to take them. And so this could be just another one of the things where if this is not done in a way that is responsible, that it doesn't foster international trust, we might actually end up in a case where attribution messes things up so much that all of the claims that we might be able to do from a purely climatic perspectives are not enough to convince people that this is a good idea or not.
Oh, hi. Thank you so much for the talk. Over here.
Sorry, Emma.
No worries. But yeah, I guess I had a quick question in terms of thinking about, deploying SRM, all these practices. We can see that historically, a lot of the time, a lot of underserved communities deal with the brunt of like climate change, right? If we think about where all the oil and gas companies are located, we can see that historically that's really kind of been affecting predominantly like low income communities.
So I guess I was wondering your opinion in terms of how we could equitably like approach this in ensuring that like underserved communities aren't necessarily the ones bearing the brunt of all the risks of all of these modifications, while also considering like kind of being able to achieve all the goals we're doing. Thank you.
Yeah, another amazing question. Thank you. So that's again part of the huge problem, right? I'll start with a story. So 3 weeks ago, there was a meeting of the United Nations Environmental Agency where kind of all the countries get together and discuss a lot of issues. And for the first time, there was actual official discussions about SRM. And there were some countries that were in favor of studying it more. And then there were a lot of countries that were on the fence or actually had negative opinions about SRM. And a lot of these countries were actually countries in the global south, were countries in Africa, Mexico, some other countries in South America. Why was that? The main reason being those countries do not trust the kind of solutions that are sometimes proposed by countries like the United States, right? So this is absolutely an issue. To me, the main way to sort of avoid this is really to make sure that whatever kind of science we do is understandable and doesn't only come from the usual suspects in the usual countries. So I work a lot with scientists in the global south to make sure that these expertise around issues like SRM, without giving moral judgment about whether we should do it or not, that there's a lot more penetration when it comes to the scientific understanding of this issue. And eventually, this is the only way, right? I understand that this is not the same in terms of international climate justice and underserved community in one country, but eventually, the main solution is more information and more robust information compared to less information. So by increasing our understanding and the way in which we can have this information penetrate, we can at least hope that these kind of questions are resolved more equitably.
Hi, I was wondering about what the actual mechanisms for like SRM are, and like what methods we would use to like inject the aerosols into the atmosphere, and like how it would be maintained over like periods of time, like over many years.
Yeah, excellent question as well. So the issue there is that I both have an answer, but the answer is hard to give because you never want to give the impression that you thought about it so much because you're proposing to do it, right? But this is sort of making headways. Of course, there are ways to do it, and the main thing would be, planes can carry a lot of stuff. And normally the thing that is more expensive and more climate damaging with planes is the fact that they move horizontally. If you were just to go up to the stratosphere, release something like SO2, which is a gas, you just open a valve, the gas goes out, you could do it. I'm not claiming we should, again, and I'm not claiming people have tested it, but there are really no technological constraint there aside from the fact that you have to build those planes. And honestly, there are planes that can carry like 100 tons of sulfate of whatever material in one go. So it wouldn't be beyond the realm of many countries to do something like that if they really wanted to. Now, you make, though, a good point about the fact that you don't just want to do a one-off, right? We know that volcanoes mess up the climate because they do it all at once. And so if you want to do something like this, you want to go at it day by day and understanding how much leeway do you have, how many days you can spend without not doing it, right? And so you need to build something that is actually a whole operation, right? Whoever is going to do it is not going to just buy a plane, buy the sulfate, and go. You have to have, an entire chain of distribution. And honestly, the answer is not many people have looked into this, but it's an incredibly interesting venue of research to understand how this would look out in a more actual, productive way.
Hi,
Hey.
thank you for speaking. I'm not too sure if this question is too related to your talk, but I'm going to ask it anyway. You mentioned how we could possibly look to SAI climate intervention in the future rather than, let's say, continuing to constantly reduce CO2 levels or other techniques of like mitigation. So I was wondering what you thought about the growing voluntary carbon market, and instead of, I guess, pushing VCM, should we be using funds to research SAI instead?
Okay, sorry, I'm not sure I got the last part of the question. But the acronym that you used, I'm not familiar. VCN, is that? I don't.
Yeah, that's the voluntary carbon market.
Oh, okay, sorry. Okay, now it's clear. That's a very tough question. There is definitely an issue with who should even pay for this research and who should do it. And my particular take on this is that for all the reasons that I listed, there is only one actor that should be thinking about climate intervention, and that actor is the state, well, possibly an international coalition of states. And honestly, compared to how much CDR is expensive and you need to figure out a carbon market, SRM is not expensive at all compared to a lot of other things that we do in the world. So I don't think that cost is as much as an issue, but I do think that research, and I work a lot to make sure that research is transparent, is publicly funded, and doesn't have, for instance, fossil fuel companies' interest in any way.
Time for one or two more questions. Hands high. I know there were more hands. There we go.
Hi. So earlier in the talk, when you were talking about different possible strategies for land carbon removal, you mentioned that a lot of them aren't really feasible on like large scales because a lot of them depend on, technologies that don't exist yet. But I was curious, what are the factors that prevent specifically like afforestation and reforestation from being a reliable like carbon removal strategy?
Great question. I would say, well, many, but two main. One, the first being afforestation or reforestation take time before, so actually, okay, three. This one, right, it takes time. So it is great. There are a lot of good reasons why we should do more afforestation, reforestation. Not all of them have to do with CO2 concentration. Actually, most of them don't. The second one being that actually a lot of the times when climate scientists do climate modeling and add more forests to the climate models, you cannot put forests everywhere. You have to put them in places where the forest would actually grow. And it turns out that those places are also places where you could grow food, right? So there's a lot of tension between food security and things like afforestation. The third one being, if you're trying to have a mechanism like reforestation or afforestation and carbon credits, it is, well, there's a lot of research actually pointing out that all of the carbon credits that have to do with afforestation are pretty close to a scam for a lot of reasons. It's incredibly hard to measure how much CO2 you're actually saving, plus what happens if the forest burns, because climate change is making fire weather worse in some regions, right? And so what happens then? Does your CO2 credit burst into flame as well? Are you forced to pay again? Nobody has solved these kind of issues. So again, there are tons of reasons why we should make sure that we have more forests and that we reforest. But really only a few of them have to do with what's the potential for them to actually reduce CO2 concentration.
Just isn't enough land area. The other big one, adding in.
I mean, ask the people in South America, right? Ask the Amazon forest and the people who live there, why not, right? Like, I think that there are plenty of examples, very good examples about that, yeah.
Thank you.
Okay, hands. You catch any? There we go. Okay.
Super quick question on public perception. Not saying that I believe in this, okay, but I do know that at some point there was like conspiracy theories going around chemtrails with planes. Now, this isn't like a widespread thing, but I am wondering how you could make sure that people see this kind of geoengineering as trustworthy instead of being afraid.
I think that's like, well, I don't know how, honestly, otherwise, no, but I honestly think that, and I get that question a lot. I get those kind of questions a lot from people who are conspiracy theories and all of that. The main honest answer is to just, point out the research you do and say, why would I be claiming something different from what, eventually, like the only way in which you can foster public trust is by being trustworthy yourself. But I don't have a good answer about that, to be honest. Yeah.
Thank you.
Okay, let's say thank you very much.
Thank you.